Okay, now we're going to do something algebraic. They're giving us a vector field that they've drawn for us. We can see that it's f of xy equals minus yi plus xj. You can see that if you follow a flow line and just follow around, you're going to see it seems to make something like a circle. Now the question is the shape of a flow line here actually a circle, or is it just something that sort of curves around like that? Well, there's a way we can address this, and this is what we do. We start like this, and remembering if this is actually a flow line, then this is actually a velocity vector at every point. Remember what a velocity vector looks like, right? We start with our vector where it says x of ti plus y of tj. Now that's not the velocity vector. The velocity vector is the derivative of that. So we take the derivative of that, and we're going to get dx dt I plus dy dt j. Now the idea is if it's an actual velocity vector, it looks like dx dt I plus dy dt j. If this is actually a velocity field, these are the velocities at every point. So this is going to be the velocity. No, this is going to be the velocity, and we can write down two equations. I can write down the equation dx dt equals minus y, and then I can write down the equation x, oops, it's right the other way, dy dt equals x like this. Now these are both differential equations. Remember from Calc 1 or Calc 2 that a differential equation is just an equation that has a derivative in it. Now what we want to do is, because it has the t's, it's hard to see what the shape is, so what we're going to do is take equation 2 and divide by equation 1. When I take the equation 2 and divide by equation 1 on the right-hand side, I get minus x over y. When I take equation 2 and divide by equation 1, it looks like the dt's cancel. The dt's actually do cancel, but that's actually because of the chain rule. The notation dx dt and dy dt was actually invented to make this look like cancellation, which is great. What we want to do is see if we can't solve for y. We're going to do this the same way you do in Calc 1. I'm going to get all the y's on one side, all the x's on the other. So, sorry, this should be dy dx. Here we go. I'm going to get y dy equals minus x dx. And now I'm going to take the antiderivative of both sides. This is just a teeny bit bogus, but it's actually valid, so I'm going to live with it. Antiderivative of y is 1/2 y squared plus some constant. Antiderivative minus x is going to be minus 1/2 x squared plus some other constant. I'm going to throw the x squared over here and the constant over there. So I'm going to get 1/2. Let's do it like this. X squared plus y squared equals some constant. And let's call that new constant k, so I get this. So finally, I'm going to get x squared plus y squared equals 2k, which is a constant. Now, if that constant is negative, this has no graph at all. But if k is positive, this is the circle that we thought it was. In other words, they gave us a velocity field. We know that if it's a velocity field, it's actually the velocity of some parameterized curve. Then we set f1 equal to dx dt. We set f2 equal to dy dt. We try to get rid of the dt. We try to solve for y. And now and then, you can actually see that the picture that we see, the graph that we see, is really the one we think it is. And that's how you would check.